Hey everyone, welcome back. In earlier episodes, you have looked at how you can change the intensity of an LED. In one instance, you connected it in series with a potentiometer, and as you change the potentiometer, the LDR brightness would vary. That's an analog way of doing things. And in a different example, you also connected an LED and an LDR to an Arduino, and then as the light intensity changed on the light dependent resistor, the LDR, the brightness of the LED kept changing. So that particular feature of the Arduino is something that's known as pulse width modulation. In the code, you would have noticed that it's written as analog write, but under the covers it is basically just digital switching on and off, because the Arduino cannot actually produce an analog signal. It can read analog as input, but it cannot really produce analog as output. So engineers did some smart thinking about how they can actually do an analog pseudo analog output using digital signals. So let's look at a little bit about signals and waveforms and so on. This is going to involve a little bit about drawing graphs and so on, but it's a good understanding of a lot of things that go under the hood in electronics. So if you know of any let's say battery operated device, let's say you have a remote control, it uses 2 batteries, so that would be at a level of 3 volts. So if I want to graph out something like that, I will start with an x-axis, which is basically the analog value of that voltage, which could be 3 volts or 5 volts, and then along the x-axis I can draw a horizontal line where I can represent what is the actual level of that voltage. So if we start at 0 volts and 0 time, and let's say this is your 3 volt level, when you attach the batteries to the remote, or when you turn on the switch to some device, or basically you do that, the voltage which has been 0 up until then rises up to 3 volts and stays at 3 volts as long as you keep it running. And when you switch that device off, it goes back to 0. So that's a signal that goes from 0 to 3 volts. And in microcontrollers, you recognize that this is what it represents as 0 and 1, low and high, and 0 and 3 volts. So if it's an Arduino, the digital IOs on the Arduino are running at 5 volts, not at 3 volts. If it's an ESP32, for example, the digital input and outputs are working at 3 volts, not at 5 volts. So a diagram like this would represent something that happens in, for example, an ESP32 when you turn on a specific GPIO and turn it off. So let's say if you are looking at the signal coming from the D13 pin, which is usually connected to the blink LED, then this is how it would look like. When it's off, it's at 0 volts, and when it's on, it's at 3 volts, and then it keeps going up and down between these 2 levels. If this was an Arduino, the same thing would, instead of 0 to 3 volts, be at 5 volts, and you'd pretty much get the same signal, but again now the value is different. So that's just basically switching voltages 0 and high, and because the high level is consistent, it doesn't change over time, it stays the exact same value it is, which is why it's known as a direct current. The flow of current is not changing directions, and this is where we can try and think of other kinds of voltage as opposed to DC, for example, alternating current or AC voltages. So let's get rid of this whole sketch and look at some typical waveforms that you would find in electronics. So one very commonly seen waveform which we have in our houses every day is what's known as a sine wave, and that's what comes in for your for running everything in your house. So the electrical power that you receive from the electricity company is some sort of a waveform like this, which is known as a sine wave. And there are a couple of things that you need to know about this waveform, as in what is its average value. So there are three parameters that define a typical waveform like this. What is its average value, what is its peak value, and what is its RMS value. And it's interesting. I recommend that you look it up and try and do some self-learning by trying to understand how different waveforms have different average RMS and peak values. But typically this is what a sine wave would look like, where it's a time variant signal. As the time passes by, the analog value of the voltage keeps changing, and this is a purely analog signal. Now, the other kind of waveform you can get is something similar but different shape, known as a triangle wave. And sometimes this can be simulated much easier using digital electronics, and can be used as with some kind of filtering to simulate something like a sine wave. So a lot of let's say appliances like, for example, inverters might use this kind of pseudo sine wave output, where they are actually generating a triangle wave and then converting it through some low pass or high pass filtering to a sine wave. So and then we finally have the classic, or the more commonly seen kind of waveforms we see in digital electronics, which is essentially a square wave. And a square wave is exactly what it says. The wave shape looks like a square. Doesn't have to be a square, it could even be a rectangle like so. So I'm showing here a signal where it's turning on and off at random intervals for random periods of time. So the on time is random and the off time is also random. So that's the triangle and that's the square wave. And you'll notice that with the sine and the triangle wave, I've drawn the waveforms as going in both quadrants, which is on the positive side and the negative side as well, but not the square wave. You can also have square wave signals that go along the zero line like this, in which case the low for the square wave would be, let's say, something like negative 5 volts, and the high would be positive 5 volts. But in this case, the low is 0 volts and the high is, let's say, 5 volts. So that's a little bit about different kinds of waveforms, and we will focus on the square wave part because this is what leads us to creating what's known as a pulse width modulated signal, and that's a good way of sort of doing pseudo analog outputs from a microcontroller. So again, let me get rid of all of this. And let's look at what a typical PWM signal looks like. So what pulse width modulation does is, you have your x-axis and you have your y-axis. It generates a series of pulses that go on and off like this. And now, depending on the ratio between the on and the off times, you can now control what is the average level of this voltage. So if you assume that this voltage is high all the time, then that's like 100% output, right? On the other hand, if the same signal is at 0 volts, then that would be 0% output, obviously. Now, what if you want something between 0 and 100%? The easy thing is turn it off for half the time, turn it off for the other half. and that frequency can be anything we choose. That is a little bit irrelevant for the current discussion. So let's say I have a third waveform where I now turn it off for a certain period, then turn it on for a certain period, then back off, back on, back off. And now these time periods are all equal, the on time and the off time. When I get this, the average value of this waveform will be 50% of whatever is the max value. So if this was 5 volts, 50% would equal to 2.5 volts. So that's a way of getting, let's say, 3 different voltage levels: 0 volts, 2.5 volts, and 5 volts. And we can now expand this reasoning to say that, let's say we want a different level. Let's say we want 75% output, in which case we'll keep it off for a short time and on for a longer time, then turn it off for a short time, keep it on for a longer time. And if we keep doing this, the average voltage level would be, let's say, 75% of 5 volts. So this technique where you use a square wave signal and you change its duty cycle. So this is the terminology used for this. Your frequency of the waveform remains the constant. If you notice the time period from the time it goes on to the time it goes on again here and over here will remain consistent. So keeping the frequency constant, we just change what's known as the ratio between the on and the off times of this signal, and that's all you need to do. And the Arduino can generate this kind of signals internally. It has a bunch of specific special pins that if you look at a pinout diagram for a Nano or an Arduino Uno or any of the others, you'll notice them marked with a little squiggly line that indicates that it's a PWM output, which is sort of the analog write or the pseudo analog output. So that lets us do a whole bunch of things. For example, you can connect it to an LED and you can now change the brightness of the LED. That's a very obvious example. And the other use for PWM signals is something that you might have used or heard of, which is known as controlling servos. So servos typically work only on PWM, and the way they work is at 50% duty cycle, they are at 0 position, and as you go below 50% or above 50%, the position of the servo keeps changing. And that's how you basically control the servo. And doing that is useful because now the Arduino doesn't have to generate an electrical power that needs to drive the motor. It just needs to generate a signal which doesn't need a lot of current, for example. So the power to drive the servo comes from the power supply, basically. And the Arduino is basically just giving a small low current control signal. And that lets you connect servos of different capacities to the same microcontroller pretty easily. Now that we've looked at some of these sketches of how PWM works, let me show you a little bit of a better representation of how it works. I have here a slide that shows you all of what I drew in a much neater and better fashion. So the first graph you see at the top is, you can see it's marked bottom 0 volts and high is 5 volts. And since the duty cycle is 0, because you have written analog write as a value of 0, there's literally no output because the voltage stays at 0. That GPIO pin doesn't turn on at all. But let's say you now write the analog write at a value of 64. That corresponds to 25% in duty cycle because analog write can have values from 0 to 255 that you see here. So we are at 64, which is 25% duty cycle. And now you'll see that the output is turning on and off, but the on time is much shorter than the off time. So the average value of this, which is the red line that you see here, is lower, and that is at 25% of 5 volts, which means it will be about 1.25 volts roughly. And then as you keep increasing the value on analog right, if you go to halfway like 127, which is 50% duty cycle, you get a proper nice square wave where the on time and the off time are equal, and you can see that the red line has risen up some more, and that value would now be 2.5 volts. And then you can keep going at a value of analog right 199, 191, you'll have 75% duty cycle, so on for a longer time and off for a shorter time. If you consider the duty cycle as 100%, then it's obvious that the on time is 75% and the off time is 25%. And then if you go all the way up to 255, then you have a 100% duty cycle, in which case the output voltage doesn't switch off at all. The average goes up to 5 volts. So that's how you get a sort of analog by using just digital signals. And here's a representation of what happens. The blue line is your analog right value. So when it reaches green, it's at 0. When it goes to red, it's at 255. And as it moves between those two values, up and down, you can notice that the duty cycle of this pulse width train is changing. And when that happens, you can control the brightness of an LED, change the loudness of a buzzer, or control the position of a servo. There are so many uses for this. It's pretty amazing use of digital techniques to do things in an analog fashion. So these are some of the two examples of where you would use PWM. You want to change the brightness of a LED, you want to control the position of a servo. You can even use it to generate or control the sound that you get from a buzzer, for example. So using just digital signals, there is no analog in this. You can just send the signal to a piezo buzzer or a speaker, and you can definitely get a certain range of sounds depending on how you control the duty cycle of these waveforms. So that's a little bit of a very quick rundown on different kinds of waveforms with a focus on PWM, because that's something that we will use a lot as we go along on our journey with microcontrollers. So till I see you again, have fun.